Okay, so enthalpy is the first part of the energetics topic, and what we're going to look at is basically what enthalpy is, and then how you would draw and interpret an enthalpy level diagram. So enthalpy diagrams, they show us lots of different things. They show us all about different amounts of energy. So if we looked at these two diagrams at the bottom, we've got a graph here that has our reactants and our products. So it's showing our reactants have a lower amount of energy than our products do, and this one would be vice versa. So have a think now which way around you think they are. Which graph is showing us, which diagram is showing us an endothermic reaction, which was showing us an exothermic reaction. So what is happening here is heat is being taken in. So as the energy increases in this first diagram, so we've got the reactants energy, and actually the energy is increasing into the products. Heat is being taken in. So if we say heat is being taken in, we say that is an endothermic reaction. Whereas the second diagram, our reactants have a higher amount of energy than our products. It shows that heat is being given out. So that means it is an exothermic reaction. That's a bit of a recap from GCSE. So enthalpy. So let's go through the key ideas of enthalpy. So enthalpy is the total energy content of the reacting materials, and we give it the symbol H. Enthalpy actually occurs in set standard conditions. So whenever we talk about enthalpy at the moment in chemistry, we say it's in a standard condition of the pressure of where this reaction is taking place has 100 kilopascals, temperature is 298 Kelvin. So we say it has a delta H standard, and H being the symbol for enthalpy, so delta H standard. So enthalpy is that total energy content of all of our reacting materials. Enthalpy change then is a term used to describe the energy exchange that takes place with the surroundings under those standard conditions I've just explained, and is given the symbol delta H. Delta is used to indicate a change in any quantity. So this one here is our delta H standard symbol. This is saying actually delta H for enthalpy change. So enthalpy change under those set conditions. We're going to describe that energy exchange between our environment, between our surroundings, and between our reactants. So enthalpy change, delta H, how to work this out? Well, we get our delta H of products, so our enthalpy of products minus our enthalpy change of reactants. And the units that we measure this in are kilojoules per mole. And that's really important to remember, it's in kilojoules per mole. So that is basically what enthalpy is. It's a way that it's all the content of our reactant materials, and enthalpy change is describing that exchange between the surroundings under those standard conditions and the reactants. So enthalpy level diagrams, they're actually very similar to those original exothermic, endothermic diagrams that we talk about at GCSE. So here's an endothermic one. So our energy level of our products is higher than our reactants, so heat is taken in from the surroundings. So we're showing here heat is being taken in, so we have our reactants here, the lower amount of energy. We need to take energy in for that reaction to occur, so we have that increase, and then we have our products here. As such, the exothermic example is the opposite. We have our amount of reactants, and it decreases for amount of products, showing our heat is given out. So energy level of our products is lower than reactants, so heat is given out to the surroundings. So an exothermic reaction, the energy released on bond formation in the product is greater than that absorbed through breaking bonds in the reactants. So what we mean by that is basically whatever energy we're releasing when we're breaking those bonds in the products, that is far, far, far greater than that is absorbed back through breaking the bonds in the reactants. So that's an exothermic reaction. So this is our exothermic, that's our endothermic again. So again, we've got our reactants, we have an energy change because we've given energy out, energy is released, and it will be done as a negative kilojoules per mole. Okay, so that is a negative sign. That's really important. So you know if your reaction is an exothermic reaction from data, is if it's a negative, because actually the amount of energy in reactants is a lot higher than the amount of the product, so we should get a negative value, a negative delta H, negative enthalpy change value. So our energy of reactants is greater than our energy of our products. So these are the most common types of reactions. So things like combustion reactions and neutralization reactions are all exothermic reactions. So these are the ones that are most common, you're most going to come across. And then we obviously have our endothermic reactions. These ones have a positive enthalpy change value. So in an endothermic reaction, the energy that is needed to be absorbed to break bonds in the reactants is greater than the energy transferred to the surroundings as bonds are made in the products. So basically, we actually need to bring in more energy to break those bonds in our reactants than what is given out when we're transferring the energy to surroundings as bonds are made in the products. And this time we've got a positive enthalpy change data point. So our energy of our reactants is less than our energy of our products. That's really important to remember. These are less common chemical reactions. An example of one is photosynthesis, is an endothermic reaction. Obviously, photosynthesis, we're talking about taking UV rays in, the process of it, that is an endothermic reaction. We don't have lots of endothermic reactions. So let's go to exothermic again. So an exothermic enthalpy change is always given a negative value. And it's given a negative value because its energy is lost to the surroundings. So the energy that's in those reactants, as those bonds break, that energy is then lost to the surroundings and does not go into the products. Therefore, its delta H will be negative kilojoules per mole. That's really important. That is the only way that you'll remember if we're getting a set of data and trying to pick out if something is exothermic or if something's endothermic, is looking for if it's a positive or negative sign. If it's a negative number, that must mean it's an exothermic reaction, because those bonds that have been broken in the reactants to make the products, that energy is then lost to the surroundings. So again, our equation is that delta H equals energy change of our products, take away our enthalpy of our reactants, so products minus reactants. And because it's products minus reactants, we would end up with a negative value for exothermic reactions. Again, if it's an exothermic reaction, we are expecting our enthalpy of our products to be a lot smaller than our enthalpy of our reactants, and that's the important part. If we have got that, then therefore it should definitely be an exothermic reaction. Again, endothermic reaction. An endothermic enthalpy change is always given a positive value, like we said before, and that is because we are gaining energy. The energy is gained by the system from the surroundings. It's taking energy in, so actually, because of this equation, our products are going to have more energy than reactants because we've taken energy in from the surroundings. Therefore, the system has more energy. Therefore, our delta H value will be positive kilojoules per mole. Because of that, just looking at it again, when we're going to do the equation, you could start to guess straight away if a reaction is going to be endothermic or exothermic, because our enthalpy of our products should be a larger number than of our reactants. Just going to see if I can get this to work. I don't know if it worked earlier. I'll keep going. So that didn't work. Okay, so here's an example of an exam question for enthalpy. I'm going to talk it through. It would also be a good place to sort of pause it later if you're going to rewatch this later, to then have a go at answering it yourself. But this is a really good example of an enthalpy question that you might get. So you get given an energy level diagram for the complete combustion of methane in air. So we've got methane plus oxygen and as our reactants. And so sometimes people like to label things like that on. That is fine. You can do whatever you want to these during the exams if it helps you. So you might want to label on your reactants. Some people do, some people don't. Again, I haven't plugged my pen in, so this isn't going to work. Okay, there we go. Undo that. So we've got our reactants here. And we've got our products here. If we remember, delta H equals our products minus our reactants. Energy level, well, we can see straight away here, our reactants have got a high energy level, so they are going to have a big number. Products got a low number, so they are going to have a small number. Small number take away big number, well, we're going to have probably an overall negative value coming out in kilojoules per mole, joules per mole, which is probably hinting at we have an exothermic reaction. So I've looked at this, and this is all the information I've gained from this diagram before I've even read the next question. And I think sometimes it's really important that we do that, actually, is that we stop and we spend some time actually just looking at this diagram, looking at what it tells us before we sort of get bogged down and too overlaid in actually what the question's asking us. Okay, so we've worked all this out. We're then told, okay, the complete combustion of methane in air is an exothermic reaction. Nice. Okay, we've just said, looking at this, it looks like an exothermic reaction because of the energy level diagram that we've got. How does the energy level diagram show that this reaction is exothermic? So this is where you want to sort of actually think about discussing this equation. So we could talk about the size of the numbers there, our energy difference, or we can show here that our energy difference will be a negative value. It'll be a negative value because we've got energy loss to surroundings. So we've got lots of ideas there. And so we could follow it up with a good answer along the lines of something like this. How does the energy level diagram show that this reaction is exothermic? So the energy level diagram shows that this reaction is exothermic because the energy difference will be a negative value as energy is transferred to the surroundings after breaking bonds in the reactants. This can be shown by the enthalpy. Oops, can't actually see what I'm typing anymore. Let's put this in here. This can be shown by the enthalpy change equation. I'm just going to put number 1 there because I'm not going to try and retype that on. I'm putting that up here as our number 1. So the energy level diagram shows that this reaction is exothermic because the energy difference will be a negative value as energy is transferred to the surroundings after breaking the bonds and reactants. This can be shown by the enthalpy change equation. Because the value of the products is less than the value of the reactants. And here we would do products minus reactants. So yes, it is only a 2-mark question, but, and this is a place where I really do think taking your time and reading the question is really important. Oh, I've just lost whatever I just wrote there, which is really annoying. Because actually what you can end up doing is you can end up just rushing through things and not actually taking the time to actually stop and spend the time in reading the question, actually answering what is being asked of you. So that is one example of an enthalpy question. Just going to clear this now and go through something else with it. Let's see if I can get to work. So mark scheme, this is what they say. Energy level of reactants is higher than that of products. Well, that's what I said in my answer. So energy heat is given out during reaction. Now, you could literally just write those 2 sentences, but what we're looking at A level is for a full comprehensive answer. So actually something along the lines of what I wrote, and I can write it here again. Let's have a go. The diagram shows that the energy level of the reactants is higher than that of the products. Therefore, energy is given out during the reaction, thus the reaction is exothermic. And that would get you 2 marks. Again, these are the extra parts that you could say, because you might have looked at that and gone, actually, well, I would have said X, Y, Z. I would have said this instead. You can say allow energy level at end is lower than at the beginning. Energy level goes down, energy change is negative. So anything along those lines you would also be allowed to say. Okay, clear that. So physical states. Okay, so whether products and reactants are solids, liquids, or gases affects the enthalpy change of a reaction. So that's really important to remember as well. So the physical state of the products and the reactants affects the enthalpy change of a reaction. So heat is put in to change a liquid to a gas. So that is an endothermic reaction. So when we are turning a liquid, when we're changing a liquid to a gas, when we're going through that state change, that is an endothermic reaction because heat is put into that system to allow that state change to occur. Whereas heat is given out of the system when a gas turns into a liquid. So that is an exothermic reaction. So that's really important to remember. So actually, if we've got, that's why state symbols on chemical equations are really important, because straight away, actually, if you saw, I'm just going to draw a chemical equation just with state symbols. I'm not even going to bother writing chemicals down. Let's say symbol A was a solid, and it becomes, because it's going through complete combustion, let's say, it becomes a liquid. Well, we know there that then energy must have got put into the system. So it's endothermic. If you were getting this instead, we might think, oh yeah, that's an exothermic. It doesn't necessarily always apply, but that is something that we can start to think about. So here's those 2. So hydrogen is a gas, oxygen is a gas, so we've got H2 plus half O2 goes to H2O as a liquid. So hydrogen gas, oxygen gas goes together, we get water as a liquid, and the enthalpy change is minus 285.8 kilojoule per mole. Hydrogen gas plus oxygen to go to another gas is also a negative. I'm now having an argument in my head. Liquid to a gas is an endo, gas to a liquid is an exo, gas to a gas is going to also be an exothermic reaction. So the differences here in the enthalpy changes represents the amount of heat needed to turn 1 molecule of water into 1 mole of steam. So it requires less energy to turn 1 molecule of water into 1 molecule of steam. Okay, so what we're going to do is, this would also be a nice place again for you to later on pause this and have a look at this. So what we're going to do is I'm just going to stop the share for 2 seconds actually, just so I can get this open a bit better so we can show this. And we're going to go through some questions actually, where we're going to do some balancing of equations. So let's open this up again. Let's share the screen again. Enthalpy, share. Okay, so first thing is we're going to balance the equations. We're also going to name the compounds or elements present in each one, and then we're going to identify each one as exo or endothermic. So let's have a look at our first one. Let's annotate this. Let's get a different colored pen. Let's get red. Let's move this out of the way so I can see. Okay, so having a quick look at this. A quick overview of this, you can see straight away our oxygens are not balanced. Our carbon is, and our hydrogen isn't. So let's deal with the hydrogens first. Well, actually, no, let's deal with the oxygens first. So we've got CO2 here. We've got 3 oxygens on this side, and we've only got 2 oxygens on this side. So yeah, actually, let's deal with, yeah, it doesn't actually matter which one. Let's deal with the oxygen first. So we need to actually have another oxygen on this side, and I'll explain why in a second. So if we put 2 H2O here, we've now got 4 hydrogen. Our hydrogen is balanced. We've got 1 carbon, they're balanced. I've got 2 oxygens on this side. I've now got 4 oxygens on this side. So actually I just need to put another 2 here, and we've balanced that equation. Name the compounds. Okay, so we haven't done lots of naming compounds yet, but if we look at some of the elements present, so we've got a hydrocarbon here. So carbons and hydrogens make hydrocarbons. So I'm just going to put hydrocarbon here. Hydrocarbon, and we don't need to name the full hydrocarbon yet because we haven't done that yet. Obviously oxygen here, carbon dioxide, and then finally water. So let's look at this. We have got a negative enthalpy change. We've got negative enthalpy change. We're going from a solid and a gas to a gas and a liquid. We've got a negative enthalpy change. That will mean it is exothermic. That means we are giving off heat into our surroundings. Okay, we've got hydrochloric acid in this one. Actually, I'm going to name them first this time. It makes more sense. So we've got hydrochloric acid, we've got hydrogen, and we've got chlorine. So we have got 2 chlorines, 2 hydrogens, 1 chlorine and 1 hydrogen. This is actually a really easy one to balance. I'm going to get a different colour pen. Just going to stick a number 2 at the front. So now we've got 2 hydrogens on this side, 2 hydrogens on that side, 2 chlorines on this side, 2 chlorines on that side. This time we have got a positive enthalpy change, which means we have got an endothermic reaction. That means energy is being put into the system, which makes sense. We're going from a gas and we're staying as gas, so we haven't got any state changes. So actually to break these bonds, we're actually going to need to put some energy into the system to break those bonds in the hydrochloric acid to be able to then make hydrogen and chlorine. Finally, we've got ammonia. Oops, no, I didn't want to do that. Let's get a different colour. We've got ammonia. we've got oxygen, we've got nitrous oxide, nitrous oxide, and we've got water. Let's look at the balancing. Okay, so this side, our nitrogens are balanced at the moment. Hydrogens definitely not. Oxygens are. So let's deal with the hydrogens. Well, we've got 3 lots of hydrogens over here. Well, I can't get 3 on this side. I could get 6. So I could put I'm having a moment there, 2, 4, 6. I could put a number 3 in front of here. 2, 4, 6. So I've got 3 hydrogens, 3 oxygens. This is going to make it horrible. 4 oxygens overall on this side. So if I've got 4 oxygens overall on this side, I could put a 2 in front of here. And let's have a look now. So we've got nitrogen, nitrogen, oxygen, 4 oxygens. 1, 2, 3, 4 oxygens. 6 hydrogens. Right, I need to put a 2 here. And now my nitrogens are out of order. So I've got 2 NH3, so now I've got 6 hydrogens, but I've got 2 nitrogens. So let's put a 2 here. Oh no, all of our oxygens are out of order now. So we've got 3, 4, 5. We don't want 5. That's an awful number to try and deal with. So let's change this. There we go. So we don't want that. What else could work? Well, we've got 2 lots of oxygens over here. Well, actually, let's get 10 oxygens overall. That would be a nice number to work with. So diagram. So it didn't work with us just putting our hydrogens at 6. What we could do is 3, 6, 9, 12 would be the next number we can use. So we can use 12 instead. So we've got 12 hydrogens on this side, 4 nitrogens. Pop a 6 here. We've got 12 hydrogens, 6 oxygens. But we need to deal with this nitrous oxide over here. Let's pop the number 4 in front of that. So overall now we've got 10 oxygens. So pop a number 5 there, and there we go. It's all nice and balanced. And you can double check 4 nitrogens, 4 nitrogens. Yep. 12 hydrogens, 10 oxygens, 4 oxygens, 6 oxygens overall. Yeah. Okay, this reaction has got a negative enthalpy change, which means it is an exothermic reaction. Oh, exothermic reaction. There we go. Again, there are our answers from before. We've got, I'll go through it now. So our hydrocarbon was methane, oxygen, carbon dioxide and water, hydrogen chloride, hydrogen and chlorine, and ammonia, oxygen, nitrogen monoxide, and water. So exo, endo, exo. For each of the reactions above, you could be asked to draw a simple enthalpy level diagram to show them. Any that would look like this would be fine. So instead of just having the reactants there, what we can do is, let's have a think. We've got methane and oxygen as our reactants on this one. I'm actually just going to write the words on this time. But what you could do up here is rather than just write randomly reactants, you could have methane and oxygen. Obviously, you'd write it with full chemical symbols, and they were reacting with, I can't remember what they were reacting with now because my brain is gone, carbon dioxide and water. So they made carbon dioxide and water. So our products were CO2 and H2O. So instead of writing reactants, instead of writing products, we can write methane and oxygen here, carbon dioxide and water there, and then we just need to put our enthalpy change in. So we would have that number, which is, oh, I can't even remember what it is now. What was it? I've gone too far. Minus 890. There we go. For it here, we'd put minus 890 kilojoules per mole. So yeah, as we go through the answer, there we go. You're basically just putting the equations in the place, and then you're just going to write on the enthalpy change over there. It is actually really important to put our delta H on, just to make sure that we're making it clear that that is an energy change. And that was my fault for not putting it on there. Okay. So that would be if we did it for the first one. Let's say we did it for the second one. I'm not going to write them all on each time. This time we're looking at an endothermic reaction. So you would draw this diagram out and you would put on for different reactants and different products. Pop them on, pop your enthalpy change on in the middle, and that would be your enthalpy diagram for that one. Then finally, what you would do is you would then do another diagram for the last one. So it would look exactly the same as the first one, just different products, different reactants, and then you would have your enthalpy change written on there. That is enthalpy. So that is where we're going to leave this. So at this point, you should be able to define enthalpy change and standard conditions. So remember, those standard conditions are the pressure and the temperature. Explain why exothermic reactions have a negative delta change, negative delta H enthalpy change, and endothermic reactions have a positive delta H enthalpy change. And then for A grades, create enthalpy level diagrams. So what we're going to look at now really quickly is, stop sharing that one, as we're going to look at Hess's law. So, oh, actually, I don't know if I'm still sharing. That's the point. Screen share, Hess's law, share. Just trying to wait for this to open up properly. I don't know if my internet's gone or something. Here we go. Okay. So what we are going to do is we're going to be able to define Hess's law, use Hess's law to find enthalpy changes that we cannot measure directly. So keyword to this is enthalpy, Hess's law, combustion and formation. What I am going to do on Monday is I will do colorimetry and bond energies with you, which will be the last of this little energetics topic. So Hess's law. Hess's law states that the total enthalpy change is independent of a route taken. So there can be multiple routes to get from one place to another. So this is route 1. That could be route 2 to get to route 1. So this is a thermochemical cycle. So we could either go direct or we can have a thermochemical cycle happening. But Hess's law states that our total enthalpy change is independent of a route taken. It doesn't matter which route we take, the enthalpy change, the total enthalpy change is always going to be the same. So we've got our enthalpy change at the top showing that it's an exothermic reaction, and that is minus 66.4 kilojoules per mole. Because it's thermochemical cycle, if we went route 2, the first energy change would be an endothermic reaction at 114.4 kilojoules per mole, and then it would be minus 180.8 kilojoules per mole overall, then get our total overall enthalpy change as being minus 66.4 kilojoules per mole. So route 2, that's how it would set out. So the total enthalpy change for route 1 is exactly the same for route 2, and that is the important part of Hess's law. That is the fact that it doesn't matter which route we take, the total enthalpy change is going to be exactly the same. Enthalpy changes of formation are really, really useful for working out enthalpy changes you can't find directly by doing an experiment. So sometimes some experiments don't allow us to basically find out the enthalpy change, so we can use enthalpy changes of formation instead. What we have to know for this is we have to know the delta H standard. So remembering that is the standard conditions that enthalpy changes are recorded in. So remember that's the 100 kilopascals for pressure and 247 for our Kelvin. for all our reactants and the products that are compounds. Our standards for elements is 0. The element is being formed from the element, so there's no change in enthalpy. So we're forming an element from an element, there is no change in enthalpy. So these are our reactants, these are our products. This would be our delta HR. These are our elements going in. These are going to be our delta HR of our reactants. That would be our route 1. This would be our route 2, finding out the products. That is because we don't know our total enthalpy change overall. So we're going to find the endo to form from the elements to the reactions, and then actually route 2 to get from the elements to the products. So step 1, what you would do is you would write the balanced equation for the reaction, and this will be our delta HR. Under the equation, what you will then go and do is write a list of the elements present. This must be balanced. So as we've got here, everything's balanced, I think. Yes, it is. Just double checking everything off the top of my head now. Yes, everything is balanced. So that's our first step. Step 3, what you're going to do is you're going to work out, you're going to find out the different enthalpy changes. So for SO2, it's minus 297. H2S is minus 20.2, and then for H2O, it is minus 286. The delta H formation values, so the enthalpy change formation values, give the enthalpy change going from the element to the compound. So basically we're looking at what it is from the element to get to the compound. So that is your step 3. So using Hess's law, therefore, route 1 will equal route 2. So if our enthalpy change going from our elements to make our reactants, and we add up the total, whatever the total for that is, should be exactly the same for route 2 going from those elements to the product. Because we're just basically missing out. Going from the reactant to product, we don't know what the enthalpy change is. So actually we go back and we look at the elements. Okay, so if the elements were going to form this reactant, for reactants, it would be this enthalpy change. Therefore, if these elements are going to make these products, it would also have the same enthalpy change, even though we've technically made the reactants and then gone to the products instead. So what we are going to do here is to work out this part, we would have our delta, our enthalpy formation change of SO2 here. We've only got one lot of SO2, so that would be minus 297 kilojoules per mole, plus 2 lots of our enthalpy change of formation of H2S, because obviously we've got 2 H2S. Add them up, that would give us our enthalpy change. Route 2, we can do exactly the same, but in the opposite direction. So we want 3 lot of delta HF of just sulfur on its own, and sulfur to sulfur, obviously we've said before, it's just going to be 0. And then 2 lots of delta HF for forming water, which is minus 286. So delta HFS is 0 again because it's an element, so it's an element going to an element. There is no enthalpy change involved. So if we then put the numbers into this, we'd go with minus 297 because that is our enthalpy formation change of SO2, plus 2 lots of minus 20.2. Other side, 3 times 0, because obviously it's 0 because we're going from an element to an element, plus 2 lots of minus 286. Step 4, actually work these out. So what we are saying is the enthalpy change of route 1 should equal the enthalpy change of route 2. We're going to work out the enthalpy change of route 1. We're going to work it out of route 2. Do those 2 equations, and actually our answer is minus 204.6 kilojoules per mole. So we're taking one away from the other because we do not know what this is. So we have to do a rearranging equation at one point. So let's get my annotations on. So we have this part coming into play. So that is this part here, because obviously we've got different bonds being broken here to form here. So we need to work out what they are. So if we did this in a calculator, we had minus 297, minus 297, and we're going to add two lots of minus 20.2. That would give us 297, 256. No, it wouldn't. 297. It would give us minus 337.4. This side, we've got three lots of 0, two lots of minus 286. So 286 times 2 minus 572. So they don't give us the same number. Now, what we have to do is we have to remember to take them away from each other to work out what this part is, okay? Because obviously that's our reactants and our products. So it's basically going back from the diagram going this, take away that, gives us our change here. So like we did when we were working out something like or endo, our products, take away our reactants, will give us our enthalpy change. So minus 572, take away minus 337.4. I'm going to double check this on the calculator just to make sure. Minus 572 minus 337.4. I did not put the right amount of minus symbols in there. Will give us minus 234.6 kilojoules per mole. That is the idea of Hess's law. Why is this not working? So, Hess's law, what you should be able to do now is define Hess's law for C grade, calculate enthalpy change for reaction if the roots and values have been given, and then calculate the enthalpy change for reaction by creating a root and using enthalpy of formation values from a data table. You are not expected to get from thin air the enthalpy of formation values. You will be given those. What I'm going to do is I'm going to send you some enthalpy questions to work through. These are actually, they're very maths based, and actually the best way to learn enthalpy and Hess's law questions are actually to have a go at working through these. So what I'm going to do is upload this to YouTube along with yesterday's, because yesterday's wouldn't upload properly for some reason. And then I am going to also email